But as Lyndon mentioned, yeah, working on the commercial experience, the consumer experience for realestate.com.au. So if you search for a property to buy, that's kind of the systems that I'm working on. So in terms of reactive streams and what I'm going to present today, so I wanted to outline a bit of a problem that we're commonly solving, how we have traditionally handled that in the past, and then our wish list for how we'd like to solve this problem elegantly. I'll introduce task, which is from Monix, an abstraction for representing asynchrony, and then I'll introduce reactive streams and then conclude. So yeah, before going into what reactive streams are, let me provide an overview of a problem that we need to solve, and then later on I'll hopefully show how reactive streams are helping us elegantly solve that. So our problem is that we've got a daily batch of 14 million properties. We need to read those from one system. So that system, our legacy system, might not be suitable for our consumer load, or the format of the data that's in that system isn't quite what we want. We then do a transformation on that data, and finally we write that back to our target system. So this is called extract transform load or read transform load, and sometimes we call these feeders at work, so I might accidentally drop in the feeder terminology occasionally. So we want to do this process of extracting 14 million properties in an efficient way, but most importantly, elegantly. So our target system for this batch job is DynamoDB. And I'll spend a little bit of time just outlining DynamoDB because a lot of people have worked with relational databases, and DynamoDB has some different complexities. So DynamoDB is a key value store, and it supports batch updates where you can give it 25 updates at once. So this will give you better write throughput than just sending it individual updates. But even though it's got batches, if you want the best write throughput, you're still going to have concurrent parallel requests at once. It's got provision, read and write capacity. So you tell Amazon how much capacity you need and they'll provision that for you. And unlike something like a database where as you increase load it might start to slow down, with Dynamo you'll have fairly linear response, but once you've hit that capacity you've asked for, it'll just reject requests. And if you're giving it a batch request, then it could partially reject half that request and satisfy the other half. So when our process starts up our feeder, so overnight we have this feeder set at a minimum write capacity of 1. So basically not paying Amazon much for that provision write capacity. But when it runs, we'll use this API to scale it up to 3,000 writes per second. And when we scale it up, then we start paying for it. But we need to start to scale it up because we've got 14 million properties. If we did one a second, it'd take days. But when we do scale it up, it's not exactly as I had it in that first graph. So we ask Amazon for additional write capacity, and it could take them up to 10 minutes to, say, go from 1 write per second to 3,000 writes per second. But straight away we're paying for the capacity they have started giving us. And we can't query how much capacity they've given us at any point in time on that curve, not curve, but whatever shape that happens to be. So we don't know how much capacity we've got in that intermediate phase. So the best strategy we've got is just to try to submit a request to DynamoDB, and if they fail and reject it because we've exceeded our provisioned capacity, then we'll just have to retry after a delay. So retries are one of the core problems that we need to solve. So I'm not going to go too much into what our legacy looks like. I'll just show one slide which gives a general feel for how we used to solve problems like this. So I've got a pointer here. We'd basically read a batch. So we'd get some data from our legacy source system. We'd then do a transformation with the source items.map, and then finally we'd write that back to our target system. And we'd do this in a loop until we had consumed all the data from our source system, and then the process is completed. I haven't shown it here, but I guess like where were you working with futures and doing batching and stuff? We're just working with low-level Scala concurrency primitives like ExecutionContext to submit jobs. And how this looks as a timeline is like this. So I don't know if everyone can see the bottom, but so we do a read. So we grab a batch. We do I'm not showing the transformations because the transformations are just CPU activity, and and very small in terms of the overall time compared to the I/O of reading and writing. We do a read of the batch, then write a batch, and read a batch. So it's pretty clear looking at that the total time our feed is going to take to execute is the combination of all of the reads and writes. So now that I've outlined the problem, I've kind of given a short overview of the legacy. What do we want going forward? So we want to be able to read from our source system and write to our target system at the same time. There's no reason that we can't do those together. And we want to be able to buffer some reads from our source system so that as soon as we've finished writing to DynamoDB, there's another batch ready to go straight away. We don't want to write and then have a delay while we go get the next batch. But at the same time, we don't want to read too far ahead of our target system because in between we're bringing that data into memory and we can't read too far ahead or we'll exhaust the finite amount of memory that we've got. And this concept's back pressure. And I'll go more into back pressure later on. And our target has limited write capacity, so rate limiting is really important for us. And we want a declarative solution as well, and not an imperative one. So by that I mean APIs that I can quite easily read and reason about, not low-level building blocks. So our end goal is to have a timeline that looks like this. So initially we'll have some reads, because we have to do reads first before we've got something to write. But then after that, we want to be reading and writing at the same time. So if we do have a timeline that looks like that, we're going to execute in half the amount of time of what we were previously. Again, these are just kind of assuming that reads and writes take the same amount of time, so I'm just simplifying it. So before I need to dive into reactive streams, I'll introduce the Monix task. And the task is a data type for representing asynchronous functionality. So it comes from a library called Monix, which is relatively new, but gaining a lot of a lot of traction. So what's important about task is that it's a lazy model of asynchronous execution. And what I mean by lazy is that when you define a task, that's all it is. It's just a definition. So in contrast to this would be eager execution. And with eager execution, you define something and you can't control when it's executed. So this is a Scala feature for anyone who's done Scala. But if something's eagerly executed, then there's several states that you need to reason about. One is, so when you're next looking at that thing, one is that it's not yet executing, or it's executing, or it's completed. So it's just a lot more to reason about in the code. And also with eager execution, your code is no longer referentially transparent. So in summary, the lazy async execution allows us to separate the definition of what we want to execute from the execution of it. So to actually define a task, we have the task plus something that we want to execute asynchronously. And in Scala, this parameter is passed by name. So the task has control over when that's actually evaluated. So a normal argument would just be, that would normally be evaluated. So if you're passing by value, that argument would be evaluated and the result would get passed by to the task. We don't want that. We want control over that being executed. So that's the simple case, but we're using AWS's library for accessing Dynamo, and that's a Java library. And it already has its own representation of handling asynchronous callbacks. So we need to adapt that to task. So I don't expect everyone to understand all the code that I've got there immediately, so I'll drill into certain little bits of it. But that's the complete code for converting from an AWS callback to a task. So if I break it down, so the bits that I've highlighted here is kind of showing what the AWS interface is. So they give you a callback mechanism, much like a JavaScript promise, where you have got on error or on success. If there's an error, you get given the error, and if it was successful, then you get the result back. And then we simply adapt that to a similar callback interface that the task provides. So we just delegate those calls on. And then finally, the Monix task also supports cancellation. And so does the Java future, which was returned by AWS. So we simply adapt the cancelable interface to that of the Java future. That's about as heavy as the code gets today, so hopefully... But I didn't want to skim over this and just kind of pretend it wasn't there. So now that we've got this representation of an AWS Dynamo task, how do we go about executing this? So on the task, we can call run async. And the run async method takes a scheduler. And here I've defined a scheduler which has 10 threads, where each thread is going to be named theta thread 0 through to 9. And then, I guess linking back to George's talk actually, the run async method takes an implicit scheduler, but given you should really only have one run async call in your code base, there's no real reason to have that as an implicit argument. You might as well pass the scheduler in implicitly. But what is the scheduler? So it's an execution context. So in Scala, that's just a pool of threads where asynchronous functionality can execute. Plus, it's got scheduling. And the scheduler is what gets provided to the task when you execute it. And because it gets provided to the task, that means the task API can now provide time-sensitive operations. And I'll go into where they're useful now. So I mentioned earlier we've got this retry problem. That period when we're dealing with, we don't know what the capacity is of our DynamoDB instance. But so we're already starting to pay for this capacity, so we want to just try to use it, but not without knowing exactly. So we have to do retries. So how do we do this with a task? So given some task, which has the logic to write to DynamoDB, we can simply call a retry function. So I've defined just a very generic retry. So this could work with anything. It doesn't have to be a DynamoDB call. But if there's an error returned from the AWS API, then we simply retry the same task, but we delay the execution by 10 milliseconds. So as I mentioned before, this kind of delayed execution is only possible because we're using the task which had the scheduler provided to it. So if you're to do something like this with a Scala future, or if you have worked with Scala future, have a think about how you try to represent the same in a declarative way. So that's pretty much all of the code for retry. Our production code's a little bit more complicated because we have an exponential back-off strategy, plus we need to handle partial retries from Dynamo. But in terms of working with the task API, that's all of it. The rest of it's just Scala specifics, and this isn't a Scala talk. So now that I've introduced task, I'll introduce reactive streams, which build upon tasks. So reactive streams are a specification of handling stream data across asynchronous boundaries. So it's just a specification. There's implementations in many languages, Java, Scala, JavaScript. I forgot to check if there was one for Haskell, but somebody else might be able to tell me. I see nods. And even within Scala, there's several implementations. And core to this is back pressure. I'll go into that more a bit later, but back pressure is honoured by this contract between publishers and subscribers. So the publisher, or the upstream publisher, must never publish more messages than the subscriber has signal demand for and subscription. So observable. So this is the Monix implementation of reactive streams. So in Scala, as I mentioned, there's other implementations. There's FS2 and Akka streams are two of the ones that I know about. So in my team, we had a look at Akka streams as well, and it's very fully featured, and it's more established than what Monix was at the time we evaluated, but it's based on top of Scala's eagerly evaluated asynchronous future. So that's why I guess I preferred the Monix reactive streams implementation, because it was based on task. And FS2, well, we've got quite a new team, a junior team to reactive streams in Scala, and we found the documentation around Monix and Akka a bit more approachable. So that's how we landed on Monix in my team. So how do we go about defining one of these observables? So this is to read the data from our source system. So if we're given an iterable, so this is just a regular data type in Scala that we can progress over to consume from our source system. We can lift that into an observable using the from iterable. So at this point, all we've got is a very similar data structure, but it's now in an observable which has additional operations for working with asynchrony and time-based. So the first thing we need to do is to transform our data. And we can do that with the map operation on our observable. And below that, I've got what's called a marble diagram. And these are really commonly used in the Reactive Streams documentation. And they just show how an operation on your observable, in this instance, behaves over time. And in our case, our transformations are all pure. We don't have any asynchronous side effects or other systems to call. But if we did, there's also a map async operation which lets us handle a transformation which might require a call to another service. So now we've got our data transformed. I mentioned we also want to have some buffering of data from our source system. But we didn't want to have our reading too far ahead of our source system compared to where our target system is up to. So I've got some fine visualizations which I built just a couple of days ago to help demonstrate this. So here we've got, what this is trying to demonstrate is that we've got a a fast consumer down here and a producer up here, and the data's kind of trickling through and there's no build-up. If our consumer slows down, then we start to get some data buffering here. And then if our consumer continues to remain slow, then data just overflows and we lose data. But in our case, this isn't what we want. So what we do want is that if our consumer slows down, we start to buffer, and then eventually that will back pressure up to a producer. So that's kind of my visualization of kind of what back pressuring is, that a slowdown here kind of trickles back up. So how do we actually go about kind of setting this up with our observable? So we just define that we've got an async boundary in our process. So this is between our source system and our target system. And we're saying on this asynchronous boundary, how we want to behave is to apply back pressure, but with a buffer of 10,000 elements. So it's also worth pointing out, I guess, that every time we're acting on this observable, there's always back pressure. So it's only when you want to customize the strategy that you need to, explicitly say, I want a different buffer size, or if you did want kind of that example I showed before where the data started to just drop off, there's a similar strategy for that where you could just drop new elements. I'm not sure what the use case of that one is. So now we've got our data read from our source system, we've transformed it, we've put some buffering in, and we now need to limit the capacity of our observable. So we provisioned DynamoDb to handle 3,000 writes per second. So on our observable, we can use the buffer time per pressure operator. And what this is saying is every second give me 3,000 elements. So if the upstream producer produced more than 3,000, it'll give me 3,000 after a second, and then the rest of it will kind of just buffer backwards and provide that back pressure. If there was less than 3,000 elements, I just get whatever it had. But what it does emit is every second there'll be a sequence containing the 3,000 elements that it's received. But DynamoDB has no knowledge of what this 3,000 elements is, so we just want to get back to a regular iterable. So we just call .flatten, and that gets rid of that nested sequence. So now that we've got, sorry, I'm losing my voice a bit. So we've got our stream now, and it's rate limited. So we're getting close to wanting to actually write these to DynamoDB. So I said DynamoDB allows you to write batches of 25 at a time. So to do that, on our observable, we can use buffer tumbling. So every element now that's emitted from our observable will be a sequence of 25 elements that we need to write to DynamoDB. And that's demonstrated by this marble diagram here, what's happening. So each one of these is just a sequence. And the marble diagram, just using an example of 3 because 25 wouldn't fit nicely up here. So far what we've got is we've defined our observable, we've done the transformation of our data, we've added some buffering in, we've rate limited to 3,000 writes per second, and we've got batches of 25 elements to write to DynamoDB at a time. So now we need to consume this observable. And the code for that looks like that. So I've got a function at the top, which is called write batch to Dynamo, and that takes a sequence of these 25 elements to write. And that's just going to use the retry logic, which we defined earlier. And then Monix allows us to define a consumer. So I'm using this for each parallel async. So what that says is that have a consumer that with I guess, a concurrency limit of 10, it'll call this, so there'll be at most 10 batches being written to DynamoDB at once. And then we call on the observable.consume with and our consumer, and that returns a task of unit. So, well, that's it, but not quite. So we've set the scene for an amazing party, but so far we've actually not done anything. So this program does nothing. So all we had been doing so far was defining this observable and transformations on it. So until we actually run that task, it's returned by the consumer operator. We've not actually caused any side effects. And this is exactly what we want. We want to only declare what we're doing, and we want to maintain control over when our side effects take effect or are executed. So, in summary, in less than half an hour, I've hopefully been able to demonstrate the basic building blocks for what previously for us were some really complex problems to solve. So while it's great that our feeder executes in less time, like in my opinion, the biggest benefit for us is code that's really easy to read and reason about. So we're defining some really complex, time-sensitive operations in a very declarative way, and the only reason we've been able to do this is because reactive streams allow us to express time and asynchrony as first-class citizens. So that's all I've got for you today. Huge thanks to the Compose organisers for putting on the event, and yeah, over to questions. Thank you.
Yeah, so maybe we'll take a question.
Yeah, so maybe I missed this preview a few slides back.
Yep.
That one.
Yeah. So it's for each parallel async, you give 10 as an argument.
Yeah.
Does it make sense that actually these can also be expanded when you get more, when you kind of ramp more computing power on this database? So is that reasonable or not?
So do you mean as DynamoDB capacity is provisioned?
Because you say, well, sometimes we scale this up and we can send more stuff to DynamoDB, but that's a 10 also increase?
So most this job only runs once a day. So most of the time we've got DynamoDB as provisioned at a capacity of 1. That's the minimum it lets you do. And then when the job starts, part of its code is to ramp DynamoDB up. So you could add some complexity in here that to say we don't need a level of 10 at a time to begin with, and then scale it up afterward, and then scale it up in feedback.
This is actually already the scaled up version, just in case.
Yeah, so this is kind of running at its capacity, I guess. Well, at its capacity, it's just running with the 10 attempts at writing to DynamoDB at once. And then internally, those tasks would retry. So that could be a different approach, is to dynamically change that number. But yeah, the task retry seemed like the simplest approach at the time I was doing this.
Alternatives, I do one way or the other way.
Yeah, I don't know about I don't know how you'd.
We have these task restarts that retries that you could also have more batches to or at least parallel processes for doing the writing in the first place.
You could potentially start it off small and load up. I don't actually know how you feed that back into the observable dynamically. Good question.
Okay, thank you, Luke.